Subject code, subject name, CEC 332 Advanced Digital Signal Processing. Unit name, Discrete Time Random Processors. Topic, Random Processors. Presented by Devi Sasikala. Objectives, Introduction to Random Process, Random Variable, Discrete Time Random Process, Stationary Random Process, Characterization of Random Process, Autocorrelation. Introduction to Random Process. Signals may be broadly classified into two types: deterministic signal, random signal. A deterministic signal may be defined by using a mathematical expression. A random signal or random process is an ensemble or a collection of signals or random variables that is defined in terms of the statistical properties that the ensemble possesses. Random variable. So what is a random variable? A random variable X is a rule for assigning every outcome S of an exponent of a number X of S. For example, of the exponent is the outcome of a die tossing, outcome of a tossing a coin. The outcome of an exponent are unknown before they are tossed. That is why the variable called random. Random variables can be characterized using probability distribution function and probability density function, which is based on outcomes of an experiment or event. Probability density function is derivative of probability distribution function. Discrete time random process. A discrete time random process is an indexed sequence of random variable or collection or an ensemble of discrete time signals. So here we have continuous time signal, discrete time signal. What is a continuous time signal? A signal is said to be a continuous time signal if it is defined for all time t, a real number. A continuous time signal can have zero value at certain instance of time or for some intervals of time. A signal is said to be a discrete time signal if it is defined only at discrete instance of time n. A discrete time signal x of n is often derived from a continuous time signal x of t by the sampling process. Stationary random process. So here the stationary is constant. So certain parameters will be constant. A random stochastic process x of t is a rule for assigning to every outcome S of an exponent a time function x of t comma s. So s refers in y-axis is outcome and t time function. If t is fixed, x of t comma s acts as a random variable. If s is fixed, x of t comma s is the outcome time function of a particular exponent. If s and t are fixed, x of t comma s is a number. Examples for random process, stationary random process: record of a speech, record of temperature, receive signal in mobile communication. Then we see how to characterize the random process mathematically. So use statistics. So first order statistics, the density function of x of t at t equal to t naught, f of x of t naught at this particular point, f of x of t naught plus 1, f of x of t naught plus 2, so on. Second order statistics, x of t1, x of t2 at t equal to t1 and t2. So we have the statistics as f of x of t1 comma x of t2. The same way, nth order statistics, f of x of t1 comma x of t2, so on x of tn. In any cases we need infinite distribution functions. It is almost impossible to specify. A random process x of t is called strict sense stationary if its statistic properties are invariant to a shift of the origin or independent to shift of origin. Let the time be discrete. We have f of x of n equal to f of x of n plus delta. So though there is a shift in this, what happens? So both are same. So we can say invariant. F of the same way, x of n1 comma x of n2 is equal to f of x of n plus delta comma x of n2 plus delta. Similarly, f of x of n1 comma x of n2 so on x of nn equal to f of x of n1 plus delta comma x of n2 plus delta comma x of nn plus delta. Except for the first order statistics, we still have infinite distributions to specify. Next, White's stationary. A random process is called White's stationary if mean is a constant. Here mean refers to expectation of x of n equal to constant eta. Expectation of x of n plus tau into conjugate of x of n is equal to r of tau. Autocorrelation function. A function is autocorrelation function. R of tau refers to autocorrelation function, and tau, how do you get this? Difference. N plus tau minus n. Difference of these two. So n gets cancelled, we'll get tau. So the function r of tau, small r of tau, both are same, and it is called as autocorrelation function. Note that r of 0 equal to expectation of modulus of x of n whole square. So it gives average power of x of n. Autocovariance is defined as C of tau equal to r of tau minus beta square. For real signals we have r of tau equal to r of minus tau. For complex signals we have r of tau equal to conjugate of r of minus tau. Thus, eta and r of tau completely characterize a WSS process. Note that the characterization of a random process by the mean and the autocorrelation function is not unique. Conclusion: in general, we can only partially characterize a small portion of random processes. In real applications, how can we know eta and r of tau of a random process? It is usually impractical to obtain eta and r of tau from an ensemble average, and we may use time average, and time average is given as eta cap of n equal to 1 by n summation n equal to 0 to n minus 1 x of n. Note that the estimation of a random variable, so cap refers to estimation. The estimation is a random variable itself, and expectation of eta cap of n equal to eta. So cap refers to estimate. Expectation of eta cap of n equal to eta. The ensemble and time average is given below graph. So S refers to outcome, and T refers to time, ensemble average, and then time average. We say that the process x of n is mean ergodic in the mean square sense if limit n tends to infinity, expectation of modulus of eta minus eta cap of n whole square equal to 0. So mean square sense, a mean square converges to the values of mean. So it is mean ergodic. If it is autocorrelation ergodic means, autocorrelation ergodic in the mean square sense means, so mean square converges to the values of autocorrelation. Characterization of random process. Characterization of random process is of two types: autocorrelation and power spectrum. Autocorrelation is a second order of a random process that provides information about how much linear dependence there is between signal values. This dependence may be exploited in the design of systems for predicting a signal. So the same way you can say for random variables. So that is how much linear dependence there is between random variables. So that dependence may be exploited in the design of system for predicting the signal. Power spectrum. It is a Fourier transform of the autocorrelation sequence and provides another representation for the second order statistics of the process. Random variable is the starting point for the development of characterization of random process. Next, so representing the autocorrelation in matrix forms. If we define autocorrelation, then autocovariance is also defined. The autocovariance and autocorrelation sequences are important second order statistical characterizations of discrete time random processes that are often represented in matrix form. For example, if capital X equal to x of 0, x of 1, so on, x of p whole transpose is a vector of t plus 1 values of a process x of n equal to 0 to p. Then the outer product x into Hermitian of x. Hermitian of x is conjugate of x of 0, conjugate of x of 1, conjugate of x of p. So x conjugate. So that outer product is given as x of 0 into conjugate of x of 0, x of 0 into conjugate of x of 1, so on, x of 0 into conjugate of x of p. So remaining the same. So this is the outer product and it is a matrix of p plus 1 cross p plus 1. If x of n is a Whitson stationary taking the expected and using the Hermitian symmetry of the autocorrelation sequence, Rx of k equal to conjugate of Rx of minus k to the p plus 1 cross p plus 1 matrix of autocorrelation values. So autocorrelation, it is defined as Rx or small rx of k that equal to expectation of x into Hermitian of x that equal to, so before you are getting this value, so apply the expectation of x of 0 into conjugate of x of 0 is nothing but r of 0 minus 0 is 0. So the same way expectation of 0, expectation x of 0 into conjugate of x of 1. So we get rx conjugate of rx of 1 and then conjugate of rx of 2, so on, conjugate of rx of 3. So rx of 1 conjugate of rx of 0, conjugate of rx of 1, so on, rx of p minus 1. Here this rx of 0 equal to conjugate of rx of 0 and here also it is rx of 0 and here also it is rx of 0. So if you see, the diagonal will be same. The same way the another diagonal also will be same. So next, properties of autocorrelation. The autocorrelation matrix of a WSS random process x of n is a Hermitian Topli's matrix where Rx equal to Topli's of Rx of 0, Rx of 1, so on, Rx of p. So if you see the diagonal before Rx of 0, that is one diagonal. Next Rx of 1, another diagonal. Rx of 2, another diagonal, so on up to Rx of p. So where the diagonals are there, that and all we are considering as Topli's. Property 2. The autocorrelation matrix of a WSS random process is a non-negative definite. So autocorrelation will be non-negative definite. So that is always greater than 0. Property 3. The eigenvalues lambda k of the autocorrelation matrix of a WSS random process are real valued and non-negative. Thank you.